Hi, this is the question about the energy transfer in the closed system. As you see that this is an aluminium cup, which is made up of metal, that is aluminium, and which have the very low specific heat capacity, and it has its own mass, that is 150 grams, whereas it contains the water. So this is a water inside. What is the mass of water that is also given? That is 300 grams. So collectively, this cup and water, this system have its own temperature, which is 20 degrees Celsius. So the question is how much ice we must put in the system. And in fact, the initial temperature of the ice is negative 10 degrees Celsius. So how much ice you have to put in this system to reduce the temperature of the system to 10 degrees Celsius. So in fact, reduce from 20 degrees Celsius to 10 degrees Celsius. Okay. So okay, students, so this is, let's say, the that amount of ice. Okay, and collectively, don't you think that this system is a closed system, because they mention here that no energy is lost to surrounding. So when there's a no energy that is going out of the system, okay, no energy that is going into the system, okay. Okay, so which means that we can say the total change in the heat of the system is zero. So perfectly, all the heat energy, thermal energy, is transferred inside the system from the cup and water to ice. So basically, ice has gained heat energy, and cup and the water have lost the same amount of heat energy. Uniqueness of this problem is that I will also draw here the temperature time graph, and we will analyze that how can we reach the right solution. So let me show you now the temperature time graph. Okay, students, so let's start from the temperature time graph, and you see that the heat energy is going from this system and the cup water to the ice. Okay, anyways, what will happen as a result of this transfer of energy? What will happen? This temperature of the water and the cup will drop. So I'm assuming that this is the 20 degrees Celsius on the scale, and that is 10 degrees Celsius, and this is in fact negative 10 degrees Celsius. So what will happen, as we don't know, we are not given also the information of time, that how much time will it take. So I am just drawing imaginary uh, of any steepness, right, of any steep line. Okay, so let's say, so you see that this line is, so it has taken some time, and now its temperature is 10 degrees Celsius. That is the final temperature of the system. But the question is that how much heat energy will be released during this process. So now I'm actually going to explain you, or I'm going to make equation of this. So this is basically the Q loss. This is a heat that is lost, okay, and is gained by the ice. So it is of course the heat of the cup and the heat by the water. Okay, and we know that the heat thermal energy is equals to mc delta t, unless it is not it in the phase change. All right, now we know that the cup is basically made up of aluminium, right? So the mass of aluminium, specific heat capacity of aluminium, and the change in temperature, and in fact the change in temperature for both is same. Okay, uh, as well as for the water, mw, cw, and the change in temperature of water. Okay, students, so let's put the value. The mass of aluminium is 150 gram, which is 0.150 kilogram, times specific heat capacity is 900 joule per kilogram per Kelvin, as well as the change in temperature is, final temperature is 10 minus initial temperature is 20. Or if you are finding out the magnitude, then that can be equals to only 20 minus 10. So plus, in the same manner, mass of water times specific heat capacity is, by the way, 4186, which is normally used as 4200 as well. Okay, and the change in temperature is once again 20 minus 10. So total will be the value amount of joules that is gone to the ice. So students, I have used 4200 because in our past papers this is mostly the case. Okay, so our answer is, important thing is that 13,950 joules of the heat that is transferred. Okay, now please don't leave the video because now we are proceeding to very important part. Now let's talk about the ice. What happened to ice? So ice will first of all absorb the heat energy and its temperature will start increasing. Okay, so when its temperature will start increasing, so I am going to start its temperature from -10, and you can see very easily that I am drawing a line starting from -10 and meeting at this point. Okay, so why I have not directly met at this point? The reason is that first the ice will reach the temperature 0 by gaining heat energy, and then it will have a phase change segment of the graph. Okay, like this. And then its heat energy will increase, its temperature will increase. I mean, you can see this is a part during which it will be a mixture of water and the liquid and the ice, and then its temperature will increase. At this point it will completely convert into the water at this point. And after that, because we are continuously, I mean, heat energy is transferred continuously, so what happen after that? Now at this point its temperature will increase, and after that, now 10 degrees Celsius is the equilibrium temperature of the system, and after this it will keep going like this. So this is a basically temperature time graph of the ice and like this whole system. So students, this ice has gained 3 times, I mean the energy 3 times. So first of all, this is a heat that it has gained, and it should be mass of ice, specific heat capacity of ice, and change in temperature. Okay, from -10 to 0 degrees Celsius. Okay, and that should be the mass of ice. We don't know about that specific heat capacity, so that is 2100. Okay, that's the specific heat capacity of ice times the change of temperature is the final minus initial, so 0 minus into -10. Okay, so we can see that it is basically 21,000 m. So once again, this is a heat that the ice has gained to increase its temperature from -10 to 0. Now we are going to the next part, and that is the phase change, right? So students, this is the time duration in which the system has a ice and water mixture. Okay, I mean, ice has not completely converted into the water. Ice has completely converted into water at this point. You see the dot. So what formula do we always apply for the phase change? That is Q is equals to MLF. It's a latent heat of fusion, and during this you see the temperature is not changing. That's why we don't see any factor of delta T. So that will be M, and the latent heat will be given to you in an exam. Don't worry about that. So it is 334,000. All right. So once again, okay, we got another. Now let's talk about now the next point. This is the time duration when the temperature of the ice has increased, or in fact the water. Okay, because it has completely converted into water. Now its water temperature has increased from 0 to 10 degrees Celsius. So when of course I will apply this equation, which equation? Q is equals to mc delta T. So basically I will take here the mass of ice, because we are talking about change of temperature of the ice that has converted into water. Okay, so that's why we will write M as it is. Okay, we are not going to take the mass of water here. Okay, this is a mass of ice. Specific heat capacity of water, 4200, and the change in temperature is final minus initial, so that must be equals to 42,000 m. Okay students, so finally, if we together, like, if we sum all of heats, so this is a total heat gained by the ice. So students, this is 397,000 m. All right, and m is the mass of the ice. So finally Don't you think that this 397,000 m is the heat gain that is equals to heat lost? So 13950 joules. Okay, so from here we can find out the mass that is equals to, you can divide these two. So student, last but not least, our answer is 0.035 kilogram of the ice, which is in fact 35 grams of ice is required to drop the temperature of water and cup from 20 to 10 degrees Celsius. I hope you understand it.